In the spring of 1977, Soviet radar installations stretched across Eastern Europe like an electronic fence, and American bomber crews knew a simple truth. Flying into that airspace meant dying. The B-52 Stratofortress, America's nuclear workhorse since 1955, showed up on Soviet radar screens like a freight train on an empty highway. At cruising altitude, Soviet S-75 Dvina surface-to-air missiles could track it from 150 miles away. The radar cross-section of a B-52 measured roughly 100 square meters, about the size of a barn door, reflecting radio waves back to their source. The physics were unforgiving. Radar works by bouncing electromagnetic waves off objects and measuring the return signal. The larger and flatter the surface, the stronger the bounce. A B-52's broad wings, vertical tail, and massive fuselage created perfect reflectors. Soviet operators could spot them the moment they crossed into defended airspace, giving missile batteries minutes to lock on and fire. During the Cold War, Pentagon war games showed that penetrating Soviet air defenses would cost 70% of the bomber fleet before reaching their targets. Those weren't acceptable losses. Those were suicide missions. The U.S. Air Force tried everything. They flew low, 100 feet above the ground, to hide beneath radar coverage, but that burned fuel, shortened range, and turned crews into exhausted wrecks. They added electronic jammers that screamed white noise across radar frequencies, but the Soviets simply built more powerful transmitters and filtered out the interference. They developed air-launched cruise missiles that could strike from outside missile range, but that required building thousands of expensive rockets instead of reusable aircraft. None of it solved the fundamental problem. The bomber itself remained visible. By the mid-1970s, the Strategic Air Command faced obsolescence. The Soviet Union had modernized its integrated air defense system into the most sophisticated network on Earth, overlapping radar coverage, computer-coordinated missile sites, and MiG interceptors guided by ground controllers. American strategists calculated that by 1985, perhaps none of their bombers would survive long enough to deliver their payload. The nuclear triad, bombers, submarines, and intercontinental ballistic missiles, was losing one leg. What the Air Force needed wasn't a faster bomber or a higher-flying bomber. They needed a bomber that Soviet radar couldn't see. Not difficult to see, impossible to see. The requirement seemed to violate physics itself. How do you hide something as large as a commercial airliner from radio waves traveling at the speed of light? The answer would require abandoning everything aerospace engineers thought they knew about aircraft design. It would require looking at an airplane not as a flying machine, but as a geometric sculpture designed to manipulate electromagnetic radiation. And it would require one engineer at Northrop Corporation to resurrect a failed idea from the 1940s and recognize that its greatest flaw was actually its secret strength. The clock was ticking. In April 1977, the Air Force issued a classified request for proposals. Advanced Technology Bomber. They wanted a subsonic, long-range aircraft capable of penetrating Soviet airspace undetected and delivering nuclear weapons. The radar cross-section requirement was classified, but engineers understood the target. Reduce visibility by 1,000 times compared to a B-52, not 10% smaller on radar, not half the size. 1,000th. Building such an aircraft would require solving problems that didn't yet have names. John Cashen didn't look like a man about to change warfare. At 42 years old, he worked in Northrop's Advanced Design Division in Hawthorne, California, surrounded by filing cabinets stuffed with rejected aircraft concepts. He had joined Northrop in 1962, fresh from MIT, with a degree in aeronautical engineering, and spent 15 years watching the company chase contracts it rarely won. Northrop was the underdog, smaller than Lockheed, less politically connected than Boeing, always scrambling for work. But Cashen had one advantage. He understood that stealth wasn't about materials or coatings. It was about shape. The concept wasn't new. In 1966, a Soviet physicist named Pyotr Ufimtsev published a paper titled Method of Edge Waves in the Physical Theory of Diffraction. American intelligence translated it, and a few engineers read it, but most dismissed the dense mathematics as theoretical abstraction. Ufimtsev had discovered that an object's radar signature depended more on its edge configuration than its size. A flat panel angled correctly could scatter radar energy away from the receiver rather than bouncing it straight back. The paper sat in Northrop's library, largely ignored. Cashen read it 3 times. He saw something others missed. If you could control where radar energy went, you could make an airplane disappear. Not literally invisible, but invisible to the radar receiver that mattered, the one pointed at you. The principle was simple geometry. A conventional aircraft has curves, rounded surfaces, and protruding components that scatter radar in all directions, including back toward the source. But an aircraft designed as a collection of carefully angled flat surfaces could redirect incoming radar waves in specific directions, anywhere except back. In early 1975, Cashen began sketching designs on yellow legal pads during lunch breaks. He calculated radar cross-sections by hand, measuring angles with a protractor, modeling how electromagnetic waves would bounce off different configurations. His colleagues thought he was wasting time. The Air Force wanted bombers that could fly faster and higher, not geometric puzzles that might not even generate lift. But Cashen had discovered something in Northrop's archives that changed everything: the flying wing. Jack Northrop, the company's founder, had spent the 1940s obsessing over aircraft without tails or fuselages, just one continuous wing surface stretching from tip to tip. He built the XB-35 and YB-49 flying wings as long-range bombers, beautiful machines that looked like boomerangs slicing through the sky. They flew, but barely. The design suffered from aerodynamic instability. Without a tail to provide directional control, pilots fought constant oscillations. The Air Force canceled the program in 1949, calling flying wings aerodynamically impractical. Jack Northrop died in 1981 believing his life's work had failed. But Cashen realized that the flying wing's aerodynamic weakness was a stealth advantage. No vertical tail meant no large vertical surface to reflect radar. No fuselage meant no cylindrical body creating radar returns. The smooth blended shape scattered radar energy across broad angles instead of focusing it back to the source. What made it difficult to fly made it difficult to detect. In 1976, Cashen convinced Northrop management to fund a small study. Could a flying wing be designed with modern computer controls to solve the stability problem while maintaining the radar advantage? The answer would determine whether Northrop even bothered submitting a proposal for the Advanced Technology Bomber. Cashen assembled a team of 12 engineers in a secure facility in Pico Rivera. They had 8 months to prove that a stable, controllable flying wing could achieve a radar cross-section smaller than a bird. The problem with flying wings was that they wanted to kill their pilots. Without a tail, the aircraft had no natural weather vane to keep it pointed forward. In turbulence, a flying wing would Dutch roll, oscillating in yaw and roll simultaneously, swinging the nose left and right, while the wings rocked up and down. Jack Northrop's YB-49 had killed 5 crew members in a 1948 crash caused exactly by this instability. The Air Force rejected the design as fundamentally unsafe, and for 30 years, that verdict stood unchallenged. Cashen's insight was that 1970s computers could solve what 1940s pilots couldn't. Modern fly-by-wire systems used electronic sensors and hydraulic actuators to adjust control surfaces hundreds of times per second, far faster than human reflexes. An unstable airframe could be artificially stabilized by a computer constantly making micro-corrections. The same way balancing a broomstick upright on your palm requires constant tiny movements. The F-16 fighter, introduced in 1974, already used this principle. It was aerodynamically unstable by design, made flyable only through computer intervention. In September 1976, Cashen's team built a computer model of a tailless flying wing with a 172-foot wingspan. They programmed simulated flight controls, and ran hundreds of virtual missions. The computer could stabilize it, but stability meant nothing if the aircraft lit up Soviet radar like a Christmas tree. The real test was radar signature, and that required understanding exactly how radio waves interacted with the wing's surface. Cashen brought in Ken Perko, a mathematician who specialized in computational electromagnetics. Together, they divided the flying wing's surface into thousands of tiny triangular facets, then calculated how radar pulses at different frequencies would reflect off each facet. The calculations took weeks, running on Northrop's CDC 7600 mainframe computer overnight when processing time was cheap. The results stunned them. A smooth flying wing, viewed head-on, produced a radar cross-section of approximately 0.1 square meters, 1,000th that of a B-52. The trick was edge alignment. Cashen designed the wing with only 4 principal edge angles. The leading edge swept back at 40 degrees. The trailing edge matched it. The wingtips angled inward, and the engine exhaust troughs aligned parallel to the leading edge. Every edge on the aircraft aligned with one of these 4 angles, creating what radar engineers call aspect independence. No matter which direction the radar looked from, it saw the same limited set of reflecting angles. Radar energy bounced away in controlled directions, missing the receiver. But there was a catch. The design only worked if they eliminated everything that protruded from the smooth wing surface. No vertical tail, no external engines, no antennas poking up, no pitot tubes, no refueling receptacles breaking the skin. Everything had to be buried inside or blended flush with the surface. The engines would need to be mounted on top of the wing, hidden inside the body, with intake ducts that twisted in serpentine curves to prevent radar from seeing the spinning turbine blades, themselves perfect radar reflectors. In March 1977, Cashen presented his findings to Northrop's executive board. He showed them a scale model carved from wood, a sleek batwing shape with no vertical surfaces and a smooth upper body. He explained that it could fly 6,000 miles without refueling, carry 40,000 pounds of weapons, and appear on Soviet radar as an object smaller than a seagull. The board gave him permission to submit a proposal for the Air Force's Advanced Technology Bomber competition. They had 6 months to turn mathematics into metal, theory into a flyable design that could beat Lockheed, Boeing, and Rockwell. Lockheed had already won. At least, that's what everyone in the defense industry believed in 1977. Lockheed's Skunk Works division had built the SR-71 Blackbird, the fastest aircraft ever flown, and in 1977 they were deep into development of a classified stealth fighter called Have Blue. Their approach to radar and visibility came from a brilliant engineer named Dennis Overholser, who had also read Ufimtsev's paper and reached a different conclusion than Cashen. Facets, not curves. Overholser's design philosophy was brutal simplicity. He created aircraft from flat panels arranged in precise angles, like a geometric crystal. Each flat surface reflected radar in a single direction. Point the panel correctly, and the radar bounced away from the receiver. The result looked like something folded from sheet metal. Hard edges, angular facets, a design so visually aggressive it earned the nickname the Hopeless Diamond. It flew in December 1977 as Have Blue, and it worked. Radar couldn't see it. But faceted designs had a critical weakness. Aerodynamics. Flat panels create turbulent airflow. Sharp edges generate drag. The F-117 Nighthawk, Lockheed's production stealth fighter based on Have Blue, could barely break the sound barrier and handled like a brick. It required constant computer correction to stay airborne. For a fighter making quick strikes, that was acceptable. For a long-range bomber carrying 40,000 pounds of weapons across 6,000 miles, it was a death sentence. Faceted aircraft burned fuel fighting their own drag. Cashen's flying wing took the opposite approach. Smooth curves optimized for aerodynamic efficiency. The leading edge blended into the wing surface in a continuous arc. The upper body fared smoothly into the wing structure. There were no hard angles disrupting airflow, no flat panels creating turbulence. The design would cruise efficiently at high altitude for hours, sipping fuel like a glider. But curves were radar problems. A curved surface scatters radar in multiple directions simultaneously, creating a broader signature than a flat panel. The solution required mathematics that didn't exist yet. Cashen and Perko developed new computational methods to model radar scattering from curved surfaces. They discovered that shallow curves, gentle transitions rather than hard bulges, could be designed to scatter radar energy in controlled lobes, similar to how a lens focuses light. By carefully shaping each curve's radius and blend angle, they could predict where the radar energy would go and ensure it didn't return to the source. The competition came down to philosophy. Lockheed argued for proven faceted technology. Harder to fly, but guaranteed stealth. Northrop argued for aerodynamic efficiency, technically riskier, but superior range and payload. The Air Force needed a bomber that could loiter over the Soviet Union for hours waiting for orders, not a sprinter that had to refuel every 2,500 miles. Range mattered more than speed. In June 1978, both companies submitted full proposals. Lockheed's design resembled a scaled-up F-117 with 4 engines. Northrop submitted Cashen's flying wing. The Air Force built full-scale radar models of both designs and tested them at classified ranges in Nevada and New Mexico. Engineers covered the models with radar-absorbent materials, ferrite-loaded polymers that converted electromagnetic energy into heat, and measured their signatures from every angle at multiple frequencies. The flying wing won the radar test. Its smooth curves, when properly coated, produced a radar cross-section 50% smaller than Lockheed's faceted design at the critical X-band frequency Soviet radars used. But the Air Force wasn't ready to award a contract based on computer models and scale mock-ups. They wanted proof. They wanted a full-size aircraft that could actually fly and actually disappear from radar. They wanted Cashen to build a demonstrator. The aircraft that emerged from Northrop's Hawthorne facility in February 1982 looked like a bathtub with wings. Officially designated Tacit Blue, engineers called it the Whale because of its ungainly bloated fuselage mounted above a short, stubby wing. It was hideous, possibly the ugliest aircraft ever built. But John Cashen wasn't trying to win beauty contests. He was trying to prove that curved stealth surfaces could fly. Tacit Blue measured 56 feet long with a 48-foot wingspan, powered by 2 Garrett ATF-36 turbofan engines buried in the fuselage. The entire upper body consisted of smooth, rounded curves blending into each other without a single hard angle. The nose curved like a dolphin's head. The fuselage sides bulged outward in gentle arcs. Even the wing leading edges used gradual curves instead of sharp sweeps. Every surface had been mathematically optimized to scatter radar energy away from ground-based receivers while maintaining enough lift to fly. The technical challenge wasn't just shape, it was materials. Radar-absorbent coatings from the 1970s were primitive, heavy, fragile, and prone to peeling off in flight. Cashen's team developed a new approach using carbonyl iron suspended in polyurethane, applied in precise thicknesses, calculated for each surface area. The coating absorbed radar energy at specific frequencies and converted it to minute amounts of heat. Combined with the curved geometry scattering what little energy remained, Tacit Blue's radar cross-section measured less than 0.01 square meters from most angles, roughly the size of a large bird. The first flight came on February 5, 1982, at Area 51 in Nevada. Test pilot Richard Thomas lifted off from the dry lake bed at dawn, climbed to 10,000 feet, and flew a gentle oval pattern while ground crews tracked him with radar. The screens showed almost nothing. When Thomas turned the aircraft broadside to the radar dish, the worst possible angle for stealth, the return signal flickered like static noise. Head-on, Tacit Blue simply vanished. Over the next 3 years, Thomas and 2 other pilots flew Tacit Blue 135 times, pushing the envelope on every flight. They tested radar signature at different altitudes, different speeds, different weather conditions. They flew mock penetration missions past simulated Soviet radar sites, measuring detection ranges. The results validated everything Cashen had calculated. A curved flying wing could achieve radar cross-sections as low as faceted designs while maintaining far superior aerodynamic efficiency. But Tacit Blue also revealed problems. The short, stubby wing generated massive drag at low altitudes. The buried engines ran hot, requiring elaborate cooling systems. The radar-absorbent coating degraded after every flight, requiring teams of technicians to inspect and repair it between missions. And the fly-by-wire system occasionally glitched, causing violent pitch oscillations that nearly killed Thomas twice. On Flight 87, a computer failure sent Tacit Blue into an uncontrolled roll at 5,000 feet. Thomas recovered 300 feet above the desert floor. None of it mattered. Tacit Blue wasn't meant to be a production aircraft. It was a proof of concept, a flying laboratory to validate curved surface stealth before Northrop committed billions to building the actual bomber. And it worked. In October 1981, 6 months before Tacit Blue's first flight, but after extensive ground testing of radar models, the Air Force awarded Northrop the Advanced Technology Bomber contract. John Cashen's team would build the B-2 Spirit. Lockheed protested the decision. Boeing protested. Congressional committees demanded explanations. But the radar tests didn't lie. The flying wing was invisible, and more importantly, it could fly far enough to matter. On February 22, 1985, Tacit Blue made its final flight and was mothballed in a hangar at Area 51, its mission complete. The contract signing on October 20, 1981, represented the largest military aircraft development program in American history. The Air Force committed to 132 B-2 bombers at a projected cost of $36.6 billion, $277 million per aircraft in 1981 dollars. Northrop's Pico Rivera facility would serve as the primary assembly site, with subcontractors Boeing and Vought building major wing sections. John Cashen was named Chief Engineer for Low Observables, the formal term for stealth. He was 46 years old and responsible for turning mathematical theory into an operational bomber. The specifications were uncompromising. The B-2 needed a combat radius of 6,000 nautical miles without refueling, enough to fly from Missouri to Moscow and back. It would carry 40,000 pounds of nuclear or conventional weapons in 2 internal bays. Cruising speed would be 0.85 Mach at 50,000 feet. And the radar cross-section requirement remained classified, but engineers understood the target. Undetectable to Soviet early warning radars until within 30 miles, giving missile batteries less than 3 minutes to react. Not enough time. Cashen's first major decision was wingspan. A larger wing meant better lift-to-drag ratio and longer range, but more surface area to keep stealthy. After months of computer modeling, he settled on 172 feet, wider than a Boeing 747. The wing would be only 3 feet thick at the centerline, tapering to less than 2 feet at the tips, creating an incredibly flat profile that would be nearly invisible from the side. The second decision was composition. Aluminum was out, too heavy for the massive wing structure. Titanium was too expensive and radar reflective. Cashen chose carbon fiber composite, layers of carbon fabric embedded in epoxy resin, cured in enormous autoclaves under heat and pressure. Composite materials offered superior strength-to-weight ratios and could be molded into the precise curves his stealth calculations required. But in 1982, no one had ever built an aircraft this large from composites. The biggest autoclave in existence was 60 feet long. The B-2's wing sections exceeded 90 feet. Northrop built new autoclaves. They constructed a 92-foot pressure vessel at Pico Rivera, essentially a giant pressure cooker capable of maintaining 100 psi at 350 degrees Fahrenheit for 16 hours while curing wing skins. Each curing cycle consumed enough electricity to power 2,000 homes. A single wing panel required 14 layers of carbon fabric precisely aligned within 0.010 inches, with technicians wearing lint-free suits working in climate-controlled clean rooms to prevent contamination. The project ballooned in complexity. The Air Force kept adding requirements: ability to deliver conventional precision-guided weapons, not just nuclear bombs; low-altitude penetration capability for missions below radar coverage; terrain-following radar that wouldn't compromise stealth; two-person crew instead of four to reduce cockpit size. Each requirement forced design changes that rippled through every system. By 1984, the projected cost had doubled to $516 million per aircraft. Congressional oversight committees demanded explanations. Classified briefings revealed the technical challenges: developing radar-absorbent structural materials that could withstand flight loads, creating engine inlets that hid turbine blades without starving the engines of air, designing antennas that could transmit and receive without creating radar spikes. Nothing like this had been attempted before. Cashen's team grew to 4,600 engineers and technicians working in secure facilities across Southern California. Security was paranoid. The project's codename, Senior Ice, appeared on no public documents. Workers couldn't tell their families what they built. Sections of the aircraft were manufactured separately so that no single subcontractor saw the complete design. The first partially assembled airframe wouldn't come together until 1987, 6 years into development. The question everyone asked Cashen was simple: will it actually work? His answer never changed. The mathematics was sound. The materials were proven in tacit blue. The design would succeed if they could just build it precisely enough. The engines were the worst problem. A jet turbine's spinning compressor blades act like a radar mirror, reflecting incoming radio waves directly back to their source. The B-2 would carry 4 General Electric F-118 turbofans, each producing 17,300 pounds of thrust, and Cashen needed to make all 4 invisible to radar. His solution was serpentine inlet ducts, S-shaped channels that twisted upward from the wing's leading edge, curving through 2 90-degree bends before reaching the engine face. Radar waves entering the inlet would bounce off the duct walls and scatter harmlessly instead of hitting the compressor blades. But S-ducts strangled airflow. Each bend created turbulence and pressure loss, reducing engine efficiency by 8%. The inlets had to be larger than normal to compensate, which meant more surface area to keep stealthy. Engineers spent 2 years optimizing the duct shape using computational fluid dynamics, balancing airflow against radar signature. The final design used curved vanes inside the duct to smooth the turbulent air before it reached the engine, recovering 4% of the lost efficiency. The exhaust was equally challenging. Hot engine exhaust creates an infrared signature that heat-seeking missiles can track from 50 miles away. Cashen designed a slot exhaust system. Instead of circular nozzles, the engines expelled exhaust through thin slots on the wing's upper trailing edge. The slots were only 4 inches tall but 10 feet wide, spreading the hot gases across a broad area where they mixed rapidly with cool air. The wing itself shielded the exhaust from ground-based infrared sensors looking upward. Then came the radar-absorbent materials. The entire aircraft skin required coatings and structures that absorbed electromagnetic energy. Cashen's team developed a multi-layer system. An outer layer of radar-absorbent paint containing carbonyl iron particles, a middle layer of honeycomb core made from aramid fiber impregnated with carbon, and an inner structural skin of carbon composite. The 3 layers together absorbed 95% of incoming radar energy at X-band frequencies, between 8 and 12 gigahertz, the range Soviet early warning radars used. The paint alone was a nightmare. It had to be applied in precise thicknesses. Too thin, and it wouldn't absorb enough radar. Too thick, and it added weight and cracked during flight. Each B-2 required 1,200 gallons of specialized coating applied by hand in temperature-controlled facilities. After every flight, technicians inspected the entire aircraft for chips, cracks, or degradation, repairing damaged sections before the next mission, maintaining the coating would consume 119 hours of maintenance for every flight hour. The wing's leading edges posed a geometry problem. A sharp edge scatters radar in all directions, bad for stealth. A blunt edge creates a strong radar return, worse for stealth. Cashen needed something in between. A radius of exactly 0.25 inches along the entire 172-foot leading edge, held to tolerances of plus or minus 0.0 inches. Manufacturing required custom tooling and laser measurement systems that verified the radius every 6 inches during layup. Even the cockpit windows broke stealth. Glass reflects radar. Cashen specified windows made from multi-layer composites, thin gold film sandwiched between layers of polycarbonate, creating a conductive coating that reflected radar while remaining transparent to visible light. The gold coating gave the windows a distinctive amber tint and cost $12,000 per square foot. By 1988, the first complete B-2 sat in Northrop's Palmdale Final Assembly Facility, a 69-ton flying wing with 930,000 parts, 500,000 rivets, and the radar signature of a hummingbird. The aircraft had no name yet, just the designation AV-1, Air Vehicle 1. Workers had spent 180,000 hours building it, fighting tolerances measured in thousandths of an inch. Outside the hangar, a crowd of 22,000 Northrop employees and their families waited in 100-degree heat for the unveiling. None of them had seen what they'd spent 7 years building. November 22, 1988, 8:30 a.m. The hangar doors at Air Force Plant 42 in Palmdale rolled open, and for the first time, the public saw what $23 billion had created. The B-2 Spirit rolled into the California sunlight looking like something from another planet. A 69-ton black boomerang with no tail, no fuselage, nothing but wing. The crowd erupted. Cameras flashed, military bands played. And in the back of the crowd, John Cashen stood with his engineering team, watching 11 years of mathematics become reality. The unveiling was pure theater, carefully choreographed to reveal nothing classified while generating maximum publicity. The Air Force showed the aircraft's exterior, but covered the engine inlets with tarps. They opened the weapons bays to display size, but kept loading mechanisms hidden. Reporters were kept 200 feet away. No one was allowed to touch the radar-absorbent skin. The actual performance specifications remained classified, but the shape itself told the story. American aerospace engineering had achieved something unprecedented. 8 months later came the real test. July 17, 1989, 6:37 a.m. Test pilot Bruce Hines advanced the throttles on AV-1, and the B-2 lifted off from runway 22 at Edwards Air Force Base for its maiden flight. Hines climbed to 10,000 feet and flew a gentle racetrack pattern over the Mojave Desert for 2 hours and 12 minutes, while chase planes photographed every moment. The flying wing handled exactly as computer simulations predicted: stable, responsive, fundamentally airworthy despite having no tail. But the real evaluation happened on the ground. At radar test ranges scattered across Nevada, Air Force technicians tracked AV-1 with the same Soviet-made radar systems they'd acquired through intelligence channels. The results confirmed what scale models had shown. The B-2 was functionally invisible at typical engagement ranges of 50 to 100 miles. Soviet early warning radars detected nothing. Only at ranges under 30 miles did the aircraft produce a faint, intermittent return signal, easily mistaken for background noise. The flight test program revealed problems immediately. The radar-absorbent coating degraded faster than expected. After 30 flight hours, sections began peeling off, requiring complete reapplication. The environmental control system that cooled the avionics bays malfunctioned repeatedly, causing cockpit temperatures to exceed 100 degrees. And the terrain-following radar, designed to let the B-2 fly automatic low-level missions at night, suffered from software glitches that sent the aircraft into uncommanded climbs. More troubling was cost. By 1990, the program had consumed $44.4 billion, and only one aircraft was flying. Congress slashed the production run from 132 bombers to 21, driving the unit cost to $2.1 billion per aircraft, the most expensive military airplane ever built. Critics called it a Cold War relic, unnecessary now that the Soviet Union was collapsing. Why spend billions on a stealth bomber when the enemy was dissolving? Cashen knew the answer. Stealth wasn't about the Soviets. It was about changing the physics of air defense forever. Any nation with radar could be defeated by an aircraft they couldn't see. The technology wouldn't become obsolete when the Berlin Wall fell. It would become more valuable. On December 17, 1993, the Air Force accepted the first operational B-2 into service at Whiteman Air Force Base in Missouri. By April 1997, all 21 B-2s had been delivered. Total program cost, $44.75 billion under 1997 dollars, or roughly $213 billion per aircraft including development. John Cashen retired from Northrop Grumman in 2001 at age 66, having spent 39 years at the company. The flying wing he'd sketched on legal pads in 1975 was now the most lethal bomber on Earth. The B-2 Spirit flew its first combat mission on March 24, 1999, over Serbia. 2 aircraft departed Whiteman Air Force Base in Missouri, flew 6,000 miles across the Atlantic, dropped precision-guided bombs on Yugoslav air defense installations, and returned home. 31 hours total mission time without a single enemy radar detecting them. Serbian surface-to-air missile batteries, equipped with Soviet-era systems designed to shoot down B-52s, never knew the B-2s were overhead until the bombs hit. One aircraft had destroyed targets that would have required an entire squadron of conventional bombers and cost dozens of American lives. The combat record proved Cashen's original insight: control the geometry, control the radar. Over the next 2 decades, B-2s flew missions over Afghanistan, Iraq, and Libya, penetrating the most heavily defended airspace on Earth without losses. The aircraft's operational availability rate remained below 50%. Roughly half the fleet was always down for maintenance, mostly repairing the temperamental radar-absorbent coating. But when they flew, they were unstoppable. Russia never developed an effective counter. Their S-400 air defense system, introduced in 2007, uses lower-frequency radars that theoretically detect stealth aircraft at longer wavelengths. But long-wavelength radar lacks the resolution to guide missiles accurately. It can tell you something is in a 10-mile box of sky, not which exact coordinate to hit. The B-2's combination of radar-absorbent materials and geometric shaping defeats acquisition radars at engagement ranges, making missile lock impossible. As of 2025, no nation has successfully tracked a B-2 with enough precision to threaten it. China studied the problem intensely after a B-2 accidentally bombed the Chinese embassy in Belgrade in 1999, giving them access to American precision-guided weapons technology. They developed their own stealth bomber, the Jian H-20, revealed in 2025, a flying wing design that looks suspiciously similar to Cashen's creation. Imitation is validation. The physics that made the B-2 invisible applies equally to any nation that can master the engineering. John Cashen never became famous. His name appears on 14 patents related to low-observable aircraft design, technical documents read by engineers, but unknown to the public. He gave no interviews, wrote no memoirs, attended no air shows to sign autographs. The engineers who worked under him describe a quiet, methodical man who preferred mathematics to publicity, someone who saw problems as geometry puzzles to be solved rather than obstacles to overcome. He died on September 8, 2009, at age 74 from complications of cancer. His obituary in the Los Angeles Times was 4 paragraphs long, mentioning his work on classified military aircraft without specifics. There was no state funeral, no presidential tribute, no Wikipedia page. The man who made the world's most lethal bomber invisible remained invisible himself, but his legacy flies. The B-2 fleet, now over 30 years old, remains the only aircraft capable of penetrating advanced air defenses with guaranteed survival. The Air Force projects the B-2 will remain operational until 2050, an extraordinary lifespan for a combat aircraft. And the principles Cashen developed, curved surface stealth, edge alignment, radar-absorbent structures, form the foundation of every stealth aircraft flying today, from the F-22 Raptor to the B-21 Raider. The bomber Russia never saw coming is still invisible. Soviet radar operators in the 1980s feared an aircraft they knew must exist but couldn't detect. Russian operators today face the same problem. The mathematics Cashen worked out on legal pads in 1975 haven't changed. The geometry that bends radar away from its source still works. And somewhere over the Pacific or the Middle East or Eastern Europe, right now, a black flying wing is slicing through the night sky 50,000 feet up, carrying 40,000 pounds of weapons toward a target that won't know it's coming until it's too late.